My name is Dr. Esther Trufan, and in this video, we will be talking about the polarity of bonds. Before we can start, we need to mention electronegativity, which is the measure of an atom to attract electrons towards itself. And the element with the highest electronegativity value is going to be fluorine at the top of the 17th group. Now, the largest electronegativity value is going to be 4.0. From there, moving through the periodic table towards the left or towards the bottom, the electronegativity value will continually decrease. In some periodic tables, you will find the electronegativity show up in addition to the atomic number, the atomic mass, and the name and symbol of the element. But this is usually not a given in every periodic table. So you may need to do a little bit of digging to find these values. When it comes to the type of bonds that can form between two atoms, it is important that we remember the definition of those types of bonds. So a covalent bond involves the sharing of electrons. And when two atoms of the same kind bond to each other, they will share those electrons equally. And that is why whenever we have two atoms of the same kind connected to each other through a covalent bond, we call that a pure covalent bond. Not because the electronegativity difference between the two is zero, but in addition to that there are two atoms of the same kind. A nonpolar covalent bond is a bond between two elements that have very similar electronegativity values. So the electronegativity value difference between the two elements is less than 0.5. Anything up to 0.4 is going to be nonpolar covalent. So here we have carbon and hydrogen. Carbon has an electronegativity value of 2.5 and hydrogen has an electronegativity of 2.1. So if we calculate the delta of electronegativity between carbon and hydrogen, it is going to be 2.5 minus 2.1, giving us 0.4. And that is less than 0.5, making the carbon-hydrogen bond nonpolar covalent. If the electronegativity value difference increases to above 0.5, then we call the bond polar covalent. And here we have carbon and oxygen. Carbon has an electronegativity value of 2.5. Oxygen has an electronegativity value of 3.5. So if we are to calculate the electronegativity difference between the two of them, we can go in either direction because what matters is the absolute value of the difference. So 3.5 minus 2.5 gives us 1.0, which is in between the 0.5 and the 1.8 values. And it shows us that we have a polar covalent bond. If the electronegativity difference between the connected atoms exceeds 1.8, then we're going to talk about an ionic compound where we assume that the electron is completely transferred from one element to another, meaning the less electronegative element will donate its electrons to the more electronegative element. In this case, calcium will give its electron to oxygen. To calculate the electronegativity difference here, we're going to take the electronegativity value of oxygen, which is 3.5. And from there, we subtract the electronegativity of calcium, which is 1.0, giving us a difference of 2.5, confirming that the bond between calcium and oxygen is ionic in nature. And it's not going to be a covalent bond anymore, but rather an electrostatic attraction between ions. So these were the rules of classifying the bonds in connection to the electronegativity difference of the bonded atoms. Here we have an example of silane, so silicon tetrahydride. It has 4 silicon-hydrogen bonds, and the first step is determining the electronegativity difference between the two. We have silicon with an electronegativity value of 1.8 and hydrogen with an electronegativity value of 2.1. So we'll start with the larger value, 2.1 minus the smaller value, 1.8, gives us a difference of 0.3. The 0.3 is less than 0.5, making the silicon-hydrogen bond a nonpolar covalent bond. There are 4 silicon-hydrogen bonds in silane, and we would write its Lewis structure like this. Each of these bonds will experience an electronegativity difference of 0.3, giving us a molecule with 4 nonpolar covalent bonds. So we don't take the 0.3 and multiply it by 4, just because there are 4 bonds. Each bond will be treated individually, and we will separately classify each bond as pure covalent, nonpolar covalent, polar covalent, or ionic.